let us start the lecture. Today in this lecture we will discuss the structure of D classes. Okay, so topic of the lecture is structure of D classes. Structure of D classes. So we begin this lecture with an exercise. Show that every D class in a semigroup S is a union of L classes and also a union of R classes. Show that every D class in a semigroup S is a union of L classes and also a union of R classes. Union of R classes. Proof. Solution of this exercise. So we first show this D is union of L classes. We show that any okay, let's begin with this. Let D be any D class. Okay, let D be any D class in a semigroup S. We show that D is equal to union of L classes, okay, of element A, where this A is in D, and we also show that this D is union of R classes. It is union of R classes of A, where A is in D. ये दो चीजें हम प्रूव करेंगे. But we prove only this first one. The other part follows on similar lines. We only show that this thing D is equal to union of L classes. The other part follows on similar lines. The other part follows on similar lines. Okay, so first we see that every D class is subset of L class. Since L class of X is always subset of D class of X for all X in X, for all X in S. So this implies if we take the union, they are also contained. They also satisfy the same inclusion. Therefore, union of L classes where X is in D is also contained in the union of D classes where X is in D. But since X is in D, so each D class is same. It's equal to D. Actually, it's equal to union of D. Is in fact union X belongs to D because each dx is D. This thing it's equal to D. Name it 1. Okay. Also this D, it's contained in union of D classes where X is in D, because this X belongs to D class of X for all X. Okay, so this thing always hold. Okay, let me write it this, not D. Let me write it here Lx actually. Lx x is in D, and reason is that each x is in Lx. Okay, for all x is true. Each class contains the element. Contains its representative at least. So combining first and second, we get combining first and second, we get D is equal to union of L classes. So similarly, we can show that D is equal to union of R classes. So that proves this exercise. Now in the next exercise, we show that the next exercise is we show that A and B are D related. So okay, this is an exercise. Let S be a semigroup and A and B be elements in S. Let S be a semigroup and the elements A, B in S. Then show that A is D related to B if and only if RA intersection LB is non-empty, and this is true if and only if LA intersection RB is non-empty. Solution. Suppose A is D related to B. This implies that what's D? D is actually L composition R. A is related to this L composition R related to B. That implies there must exist C in S such that A is L related to C and C is R related to B, which implies that C belongs to LA and this C also belongs to LB. Actually, this is if and only if. You can write here if and only if. Okay, if and only if this C belongs to LA intersection. So that proves part 1. The other part follows on similar lines. This is a very simple. Okay, next we use we introduce egg box, which is introduced by actually Guilford and Preston in 1961. What's egg box actually is? Suppose as we know that every D class is a union of L classes and R classes. So this is your actually set of all the elements which are in D. Okay, it may be an infinite set. And each cell actually okay, it's like this. So the elements in these boxes, they are the elements are D actually. Okay, and each column and each row represents actually R class. So these are R classes. Okay, rows are all classes, and these columns, they are L classes, and we know that D is union of these R classes. Okay, so D is whole, D is this, and also D is the union of L classes. So on this side you can see it's actually D. So elements of D can be distributed in this box. That box we called the egg box. Okay, and each cell like this is the cell. So these we call the cells. Each cell represents the intersection of R class and L class. It's the actually H class. Okay, this cell is H class. Each cell is H class. So suppose we have an element A here. It means that this class, the elements in this row are, this is LA actually. So इस रो में इसमें जो भी elements है ना, so that set is actually LA. इसी तरह से अगर आप इसको देखना चाहोगे, this is RA. Okay, this column is RA. Not the row is RA actually. The row is RA. This is RA, and this column is LA. Okay, so this is the egg box. Okay, in which each row represents R class and each column represents L class and each cell represents H class. So these are the elements of D which can distribute like this, because as we have seen that each D class is a union of L classes. Okay, so these are elements of actually certain D class. So because the semigroup S is the union of D class actually, so we can distribute all the elements of S in this box actually. So there is this is one D class, then we can add one more D class, then we can add one more D class, so that we can accommodate each element of the semigroup S in this box. This egg box may be infinite in case the semigroup is infinite, and this egg box may also contain single column. This may be true. Okay, also this egg box may contain single row as well, or single cell as well. If the semigroup is consisting of a singleton set, then it's a single element. Or if the D class is consisting of single element, then this egg box is consisting of a single cell in that case. Okay, now we define translation maps that we call left translation and right translation. Okay, so first we define those mappings, then we will see the properties of those mappings. And those properties actually they are provided by Green's, and those results are called Green's lemma. So let's first define translation mappings. So if we have a D class, if D is an arbitrary D class, if D is an arbitrary D class in a semigroup S, in a semigroup S, and if suppose A and B, they are in same D class, they are D related, or such that they are equivalent. Okay, they are D equivalent, but D is a union of R class. Okay, suppose they are in single row. Okay, they are R equivalent. So in egg box it means that they are in single row. Okay, so that these elements are in the same row. Then we define then by definition of R, then by definition of R we can find two elements. There exists S dash in S1 such that its R relation for element S and S must be on R right side. Its AS is equal to B and BS dash is equal to B. Now the mappings, okay, rho S and rho S dash, they are defined from S to S, defined by image of any element X, okay, under this rho S map is equal to XS, it's the right translation, and image of X under rho S dash is equal to XS dash where X belongs to S, are called right translations, are called right translation, okay. So these are right translation maps. So basically these mappings, they map A onto B because image of A under rho S is AS, this AS is equal to B here, so it maps A onto B. And same this rho S dash, it also maps B onto A, not A onto B, but because image of B under rho S dash is BS dash, which is equal to A by star, okay. So by star you can see that rho S maps A onto B and rho S dash maps B onto A. In a similar way, we can define a left translation if these elements A and B are L equivalent. In case that in egg box they are in the same column. If A is L related to B, then there exists T dash in S1 such that TA is equal to B and T dash B is equal to A. This is a double star, okay. Now based on these equations we define maps, define lambda T. It's we use another notation, that's lambda, okay, lambda T. We define lambda T and we define lambda T dash from S to S by, this is X lambda T, it maps X onto Tx, okay, and this lambda T dash, it maps X onto T dash X, or left translations. Maps, so that's the right here, maps A and B onto A and B onto, what's the image of A under rho T? It's equal to T, A is equal to B, and second it maps B onto T dash P, which is equal to A respectively. It's by star, okay, by double star. So these are two mappings, and based on these two mappings, right translation and left translation, we have two lemmas called the Green's lemma. Let's first state Green's lemma, then we will state the second Green's lemma. So which actually follows on similar line as the Green's lemma 1. So now let's state those lemmas. Green's lemma. Let us first prove the Green's lemma for if the elements are equivalent, and we have seen that A is the image of B. So A and B are equivalent maps, and image of A under this translation is B. Okay, are equivalent. Oh, the statement of the lemma is let A and B are equivalent. Let A and B be are equivalent, are equivalent, okay, in a semigroup S, in a semigroup S, and let's we can choose two elements and let S dash belongs to S1 such that AS is equal to B and BS dash is equal to A. Then the right translation is that we already defined it. Then the right translation is then the right translations, then the right translation is rho S, it's a map on S, we restricted this rho S to LA, okay, rho S restricted to LA and rho S dash restricted to LB. These are inverse of each other, and that means they are actually bijections, okay. If the inverse exists, are mutual inverse, are mutually inverse, or they are inverse of each other, are mutually inverse, or class preserving. So I will explain what this, what do we mean by are class preserving, or class preserving bijections. First is from LA on to LB, and second is from LB on to LA. LB on to LA respectively, okay, respectively. So let's try to prove these mappings. Okay, proof. We have x rho s is equal to xs for all x in S. This implies a rho s is equal to as, that's equal to b, because as is equal to b. So therefore rho s maps a onto b, where these a and b are equivalent, okay, are equivalent. Now we show that next we show that if x belongs to, if x is an element of S, and let's suppose that this x rho s, which we say it's equal to y, it's equal to xs, suppose it's equal to y. Next we show that if x is equal to, x belongs to S and x rho s is equal to S, suppose it's equal to y, then x is r equivalent to y, that is rho s is r class preserving, that is इसी का मतलब है कि rho s r class, let's rho s is r class preserving, यह प्रूव करेगी फर्स्ट, इट्स r class preserving. अगर x डोमेन में है, इसकी इमेज जो होगी सपोज वो y है, एक्चुअली इसकी इमेज x ऐसे बाय डेफिनेशन ऑफ rho s, अगर हम उसको y से डिनोट करेंगे, we will show that x and y there are so are equivalent. They are equivalent. X is not in S, sorry, it's in L, okay, it's in L. जब हम इसको एल ए पर रेस्ट्रिक्ट करेंगे ना, उस केस में आर क्लास प्रिजर्विंग है. एक्स इज इन एल क्लास ऑफ ए के. एक्स इज इन एल ए. So since this x in L is, since x belongs to LA, that means x is related to A. So there exists some u in S1 such that L related. So that element must be on left side L related. Okay, L related. So that means there is u in S1 such that UA is equal to x. Okay. UA, there is another element, but we are not interested in that element. We are interested in this element U only on the one equation. So this UA is in L A. Okay. Okay, we want to show that this is R class preserving. Okay, we need to show that this map is actually R class preserving. So x and y must be R equivalent. Okay, x and y must be R equivalent. So we have this y is equal to, we have y equal to xs, and there should be y is equal to xs. There should be y. There should be element. There should be one more element, not only one element. There should be another element. But this y dash is equal to x. I think y dash by the definition of rho s dash. So actually we don't need this thing. We don't need this actually here. We can apply both the translations simultaneously here. Since this y is equal to x rho s, that's equal to xs, and the image of, and what's this y rho s dash? Let's see this y rho s dash, that's equal to y s dash, and this y s dash is equal to x. Y s dash is equal to x. Okay, so y equal to xs and y s dash is equal to, that's we have this, we can say this xs is equal to y and y s dash is equal to x. So what's why this y dash is equal to x? Because by definition of rho s dash, it maps x onto xs dash. That's this, it maps x onto x. So that means it maps y onto y s dash, where this y s dash, it maps y onto y s dash. Okay, that's y onto y s dash. That you can easily verify. Y maps onto y s dash, the image of y. What's this? X rho s is equal to y. Actually, we have this x. This is given. Okay, x rho s is equal to y. But what's y s dash? Now let's see the y s dash. Let's apply rho s dash both sides. X rho s dash. This is equal to y rho s dash, but x rho s dash, this is equal to y rho s dash, so take it at easy. It is x rho s is xs, x rho s of rho s dash, okay, x rho s of rho s dash. Now this thing, this is equal to x s s dash, x s s dash, this is x s s dash equal to y s dash, okay. But since x is where is x is in LA, so there is some element u that actually that's necessary here. There is an element u in S1 such that this x is equal to, the element must be on left side. Actually this x is actually ua s s dash is equal to y s dash. This as is b, okay, it's u b s dash which is equal to y s dash, and this implies b s dash is a, it's again ua is equal to y s dash, so which implies ua, what's ua is x, so x is equal to y s dash. So this is actually simple. This y is equal to x rho s, which is equal to xs, and y rho s dash is equal to y s dash, that's equal to x. So that you have verified here. Since you can say, you can write here since should write here since this x, it belongs to LA, it implies that there exists u in S1 such that this ua is equal to x. तो इसका यूज करके, so then this thing happens, then this y is equal to x rho s dash xs and y rho s dash is equal to y s dash is equal to xs is equal to x. तो ये मैंने यहाँ पर एक्सप्लेन कर दिया, कैसे ही आ गया. तो मैंने सिर्फ x का वैल्यू सब्स्टिट्यूट किया, x इज इक्वल टू ua फॉर सम u in S1, तो उससे आपके पास ये आ गया y dash is equal to x. तो y equal to xs, that's the image, आपने उसको y से ही डिनोट किया. So therefore x and y, they are actually are equivalent. X and y are equivalent. So thus rho s is R class preserving, Now next we show that rho s restricted to LA and rho s dash restricted to LB are inverse of each other, are inverses of each other. For this we first show that rho s maps LA onto LB. We first show that rho s restricted to LA, it maps LA onto LB, and rho s dash restricted to LB, it maps LB onto LE. So let's choose an element. Let x be in LA. So that means x is L related to A, but the L relation is right compatible. It means that xs is related to as for all s in S. This implies xs is L related, but as is B, which means that xs belongs to LB. So what's xs actually? It's the image of x under rho s. It belongs to LB for all x in LA. Okay, so this thing is done. Next we show that when rho s dash restricted to LB, it maps LB onto LE. Okay, that's again simple. Now let x belongs to LB, so that means x is L related to B, okay, which means that x s dash is L related to B s dash for all, for every s, for every s actually. For every s dash, okay, we don't need here for every s dash, for that particular s dash, okay, because this s dash it belongs to s, it's not इससे पहले जो आपने लिखा ना वहाँ पर जो आपने लिखा फॉर ऑल एस, आप एक्चुअली ये एस ऑलरेडी हमने डिफाइन किया as this s dash it belongs to s, which is subset of s1. So and this L is left right compatible, it's right compatible. That means x s dash is L related to bs dash is A, which implies x s dash means the image of x under row s dash it belongs to LA for all x belongs to s. So इससे पहले मैं ये लाइन लिखना चाहूँगा x s dash it belongs to LA, then you write this. So therefore when row s dash is restricted to LB, it maps it restricted to LB, okay, restricted to LB, it maps LB onto LA, LB onto LA. तो अब आपके पास दो मैपिंग्स है, ओके, नाउ यू हैव टू मैपिंग्स रेस्ट्रिक्शंस एक्चुअली, रो एस which is a map from LA to LB and रो एस dash it's a map from LB to LB. अब हम प्रूव करेंगे they are inverse of each other. So we first show that this row s dash it's equal to, when we restricted these mappings on LA and LB, it's a row s is a map from LA to LB, row s dash is a map from LB to LA, so the composition is a map from LA to LB, its identity map on LA, and row s is a map from LB to LB, and we'll show that this is identity map on LB. So for this, let's choose any element in let x belongs to LA. So that means x is L related to A, so which means that there exists U in S1 such that U must be on left side, UA is equal to x. Now let's find the image x row s dash, that's equal to xs of row s dash, which is by definition again xss dash. हम प्रूव करेंगे ये x के ही बराबर है, okay, we prove that this is equal to x. What's x? X is equal to UA, ये वैल्यू हम सब्स्टिट्यूट करेंगे, this is equal to UA s dash, and this is equal to U s dash. We don't need to insert these brackets here because semigroup is associative, so without brackets it can be bs dash, but bs dash is equal to A, that's equal to UA is equal to x. So thus for all x in LA, x row s dash is equal to x, its identity, so which implies that row s dash is equal to identity on LA. Similarly, row s is identity on LB. Similarly, row s is equal to identity on LB. So thus row s restricted to LA and row s इनका इनवर्स एक्सिस्ट हो रहा है एक्चुअली, अगर हम इनको रेस्ट्रिक्ट करेंगे, रेस्ट्रिक्ट टू LB are inverse of each other, or inverse of each other, and hence bijections, and hence for our class preserving भी है, hence bijections, they are also R class preserving. So that proves the Green's lemma 1. इसी तरह से आपके पास Green's lemma 2 है, second Green's lemma also, second Green's lemma 2. Let's see this Green's lemma 2. That's for left translation, okay? Let A and B be L equivalent. Let A comma B be L equivalent elements in a semigroup S. Elements in a semigroup S. Elements in a semigroup S. Okay, and let's take two elements, and we have two elements that exist actually because of L equivalence. T comma T dash, they are in S1 such that TA is equal to B. TA is equal to B, and T dash B is equal to A. Name it double star. Then the left translation is, then the left translations lambda T restricted to R. Here is the R, okay, not L, and lambda T dash restricted to RB, or they are also inverse, mutually inverse, L class preserving, or mutually inverse L class preserving bijections, okay, from bijections from RA onto RB, RA onto RB, and RB onto RA respectively. The proof follows on similar lines, so that's an exercise for you. The proof is an assignment, okay? So you do this proof. This proof is an assignment. इसका जो प्रूफ है वो आप असाइनमेंट में के फॉर्म में सबमिट कीजिए. Now we have the combined effect of these two lemmas, the combined result. So we have the combined result now using these two parts of Green's lemma. Combined result. What's that? That's the following lemma. If A and B are D equivalent, if A and B are D equivalent in a semigroup S, in a semigroup S, then cardinality of HA, that means there is a bijection from HA onto HB. Actually, cardinality of H class of A is same as the cardinality of H class of B. This is the lemma. This is the combined lemma actually. Proof. So suppose they are H related. Suppose A is H related to B. This implies that A is, what's H? H is not H, they are D related, sorry. So this is the D relation here. So D relation. So this implies A is L composition, or you can say R composition. We'll use first R here. R composition, they are commutative actually. or composition L related to B. So therefore there exists some C in S such that A's are related to C and C's L related to B. So we show that now we show that this right translation rho s, when it's restricted to HA, it's a bijection from HA onto HC. Okay. Okay, it's a bijection. So let's choose an element in HA. Let X belongs. So this is 1 1 obviously because it's 1 1 on LA. So H is substuff HA substuff LA. H is substuff LA. Okay. So it's 1 1 map, bijection map from LA onto LB actually. अब आपको प्रूव करना HA onto HC भी bijection है ये. It's bijection from HA onto HC. So let's choose an element in HA, so which implies that X is H related to A. That means X is L intersection R related to A. So which means that X is R related to, sorry, it's C here, not, yes, it's A. Okay, X is R related to A and X is L related to A. So from this R equivalence, you have seen that this implies the image under rho s. This implies X rho s. This implies X rho s belongs to LA. But we want to show that X rho s belongs to LC. Okay. Okay, this is here A and C are equivalent. Okay, X is in HA, yes, but this is A's are equivalent because X and C they are related. Okay, A and C are related actually, A and C. So that means this now this means that X is, this implies X is R related to C. X is R related to C and X is R related to A. Okay, and this is what's this? A is L. This A is R related to C. Okay, but A may not be. A is this A. It's X is L related to A, but A is R related to C. Okay, so we have just said this L related. Okay. Now this X is R related to C. So X is in RA, or you can say it's in RC. A is R related to C. Okay, so I want to show that the image A and C are actually R related. So the image is X and its image, they are also R related. I want to prove that the image is in the image should be in what AS is equal to AS is equal to C actually. So let's see it here. Okay, let's तो since इसका नाम आप कुछ रख दीजिए यहाँ पर, नेम इट 1. Since A is R related to C, this means that there exists S dash in S1 such that this AS it's equal to C and CS dash is equal to B. इसका नाम आप 2 रख दीजिए. Now X is R related to C by 1 and our relation is X is also L related to A, and this L relation is right compatible. So by 1 XS is L related to AS because the relation L is right compatible. So what's XS? It's X rho S. Okay, so it belongs to LAS. LAS is equal to C. It belongs to LC. So XS belongs to LC. XS belongs to LC. We show that it's also in RC. That's very important. It's also in RC. XS is also in RC. So XS is in LC. Now again this A and C, they are equivalent. And the map rho restricted to LA, in particular HA. HA is actually subset of LA. It is R class preserving. That means if we take element X and its image, since rho S restricted to HA is R class preserving, so therefore X and is R related to X rho S, that is X is R related to XS for all X in HA. So in other words, this XS, the image of X under rho S, it belongs to the R class of X because they are related. But R class of X is same as R class of A. XS belongs to RA because A is R, because you have chosen X in HA. X was chosen in HA. Because X is in HA, so that means this X is R related to A. Okay, this is R related to A because X is in HA. So where this X is in HA, okay, it is in HA. So XS, it belongs to RA also. Rx is equal to RA, but RA is equal to RC. Okay, this means XS belongs to RC. Why? Because A and C are related, which means that R class of A is same as R class of C. Okay, R class of A is same as R class of C. So XS also belongs to RC, XS also belongs to RA, which implies this is also in RC, okay, RC and LC. So therefore X rho S belongs to LC intersection RC, which is equal to HC for all X belongs to HA. So thus rho S restricted to HA from HA to HC is a bijection. Similarly, you can see this rho S dash not rho S dash, it's lambda T now, after lambda T, because they are now L related, okay, not R related. Similarly, lambda T, okay, That is the second part of Green's lemma. Similarly, lambda t, or you can prove it directly here, जैसे मैंने first part इसका prove किया. Lambda t restricted to HC, from HC to HB is a bijection, और यहाँ पर actually C is L related to B. Okay, so let's compose these two mappings. Therefore the composition rho S, then lambda t. Okay, this is a map from HA to HB by restricting it on HA. It is a bijection, this map is a bijection. This is a bijection, and hence cardinality of HA is same as cardinality of HB. They are same. Okay, so let's now end this lecture here. In the next lecture we will see the properties of these lemmas. In fact, we will show that if H is an H class of a semigroup S, then either H square intersection H is empty or H square is equal to H, and in that case we will show that the H class, if it's non-empty, it's a subgroup of a semigroup S. That's the importance of these lemmas. So we will show that H class, in case H class of a semigroup S is non-empty, then it's